Hello everyone. The title of this video is Identifying Exponential Functions. Now, in this video, I'm going to be going over several examples related to this topic. Each example I'm going to be doing is taken directly from a free online textbook taken from openstacks.org. I'm in their Algebra and Trigonometry text, section 6.1, called Exponential Functions, and I'm underneath the heading Identifying Exponential Functions. Now each example I do will be either one of the examples from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Alright, so before I get into the examples I'm going to do, I'm going to just kind of go through this little part of the section here. Where they're defining an exponential function. Some keywords you're going to see in problems that'll let you know you're dealing with exponential functions. Some examples here for you. I'm going to leave this for you to read if you're ever at this particular site, this particular text. And I do want to point this out for some examples I'm going to be doing later. You've more than likely seen a linear function. The graph is a straight line. Anything that grows linearly or has linear growth refers to the original value from the range increases by the same amount over equal increments found in the domain. So when I'm talking linear growth, that means if I increase the input by 1, the output will increase or decrease by the same amount every time. Right, and you've seen that with slope, right? The slope of a line, that's what that is. How much, that amount that the output will increase or decrease when I increase the input by 1. Now, exponential functions either increase or decrease by the same percentage when I increase the input by 1 every time. Okay, so linear functions increase or decrease by the same amount when you increase the input by 1. Exponential functions increase or decrease by the same percentage when you increase the input by 1. Alright, and you'll see what I mean when we get into some examples. So down here they go through another example that you can read on your own. But I wanted to get to this box here. All right. So the definition of an exponential function. So for any real number x, an exponential function is a function with the following form. And I'll probably be writing this out as well on paper. But we have f of x or y equals a times b to the x power, where a is a non-zero real number called the initial value. It's the output when x is 0. So very often the exponent x is representing time, might even be represented by the letter t. And when time is 0, that's when you have your initial output, initial value a. B, right, the base on the exponent, you have b to the x power. B is any positive real number that's not 1. Right, because 1 to any power is going to be 1. That would be an uninteresting exponential function. But b, the base, is a positive number. All right, that's key. We'll talk about what happens when the base is negative and how we don't consider those in our talks of exponential functions. The domain of f is all real numbers. Remember, the domain is what you can plug in for the input, plug in for x. So you can plug in anything to the exponent, right? The reason these are called exponential functions, by the way, is that the input variable is in an exponent, right, in a power. The range of f is all positive real numbers. If a is positive, right, if this number a, this initial value is positive, but that flips over, and the range becomes all negative real numbers if a is negative, right, if I have a negative number as the initial value. The y-intercept is the point 0, a, and it has a horizontal asymptote. Right, the graph on one end, anyway, you'll see, we'll look at the end behavior for these functions. On one end, the graph will approach the line y equals 0, will approach the x-axis. Alright, so some swift examples of this. Let me just show you. And I'm going to there's a free online graphing calculator, desmos.com. I just put in what they had there, f of x equals a times b to the x power. And we can add sliders for a and b. I'll just do for both of them. And again, we want b to be a positive number. So I'm going to change the scale here on b to be from, say, 0 to, I don't know, 0 to 50. We'll just increase it by 1 each time. And now a can be any non-zero number. All right, so I'll stick from negative 10 to 10 here. Now, remember, we said b, the base has to be a number other than 1. Right now it's 1, so you see it's very uninteresting. The output is always 1. When a is 1 and b is 1, it's just y equals 1, the horizontal line. That's not interesting. But if I change b to 2, and then you see this graph here, they would say that this has exponential growth. As x increases, the output increases, the output grows. And like I said, it grows by the same percentage for each increase in x. When x is 0, the output is 1. Right? And then when you increase x by 1, the output is 2. You get 100% more than when x was 0. Right? You double the output when you increase x by 1, or you get 100% more. And that happens every single time. When x is 2, you have an output of 4, which is 100% more than 2. 2 plus 2, 2 times 2. Right? And when the input is 3, the output is 8, which is 100% more than 4, or double 4, 2 times 4. And that happens for these exponential functions. When an input is increased by 1, every single time you do that, the output increases or decreases by the same percentage each time. Alright, and let me put in the y equals 0 as well. That purple line, I'll make it like a dashed line, so it's not really there, but you can see it. Alright, the x-axis. And you see on the left end, the graph is approaching. It's actually never equal to 0, the output. See that red line, the red graph is above the purple dashed graph as you move to the left. I mean, it looks like it's touching, but if you zoom in close enough, it's not. So you see the domain, like I said, the domain is all real numbers. The range here is all positive numbers, right? Everything above 0 is in the range. You have a horizontal asymptote of y equals 0. The graph is approaching y equals 0 on the left end, right? Not on the right end. On the right end, the graph is going up forever, right, to infinity. But as soon as I make a negative, right now the value of a is positive 1. If I changed a to negative 1, you see how the graph flips over the x-axis, and now the range is all negative numbers, right? Everything below 0 is in the range. So this is y equals negative 1 times 2 to the x power. but still follows that exponential model. When I increase x by 1, the output, again, technically gets doubled or increased or decreased by 100% each time. And you'll also see, let me go back to a equals 1 here. As the value of the base increases, the value of b increases, it just gets really, 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 really steep. As the value decreases, it gets less steep. And in fact, let me change this up again. Let's go 0 to 10 and have it go by tenths or something. Right? In fact, what you're going to see is that when b is bigger than 1, when the base is bigger than 1, you have and also a is bigger than 1, or a is positive, you have an increasing function. But when b is less than 1, so see I have b is 0.9 here. See how it's now a decreasing function? Now the graph is approaching the x-axis on the right end and going up forever on the left end. 0.8, 0.9, 0.8, 0.7, right? It's a decreasing function in this case. Right. So just keep all this stuff in mind. It's a lot to remember, I understand, but you have a times b to the x. A is just not 0, right? And b has to be positive, right? I'll show you in a little bit what happens when b is negative. It gets messy. We're not going to consider that an exponential function. And we see that when a is positive and b is bigger than 1, the function is increasing from left to right. And when a is positive and b is less than 1, but still positive, the function is decreasing from left to right. And you have the x-axis as a horizontal asymptote and all that. And when a is negative, you just flip it over the x-axis, right? It just flips it over the x-axis. Okay? Alright, so that was a lot. That was a lot for the introduction. But now let's get into some examples. Right? Now the examples related to this objective here are, can you identify, if you're given a function, if it's an exponential function or not? Alright, so I'm going to write up the same stuff that they had in that box. So here I have my first examples. Is just which of the following are exponential functions, and I'll write up again what that meant. F of x equals, or y equals, a times b to the x power, where a is not 0 and b is positive. Right? That's what it meant to be an exponential function. And you could also add something to this, like plus 5, plus 4, minus 3. Adding a constant will just move the graph up and down. It'll still have the same shape. It's just going to move the graph up and down and change where the horizontal asymptote is. Hopefully you remember your function transformations from an earlier chapter in this text and earlier videos of mine. Alright, so let's take a look here. The first example, f of x equals 4 to the 3x minus 2 power, or 3 times the quantity x minus 2 power. Now this doesn't look exactly like this yet, but there's a numerical base. Right, there's a number base, a numerical base, and there's a variable to the first power. Notice it's just x to the first in the exponent here in this basic description of an exponential function that we're going to be dealing with. There's a variable to the first power, but I'll just say variable exponent. So this actually is an exponential function, even though it doesn't look like exactly this form yet. Now we can turn it into that form. Right, we can use some properties of exponents, which I'm assuming you know from previous videos, previous studies. You can use the properties of exponents to change this to look like this form. If you can take your function and actually make it look this way, a times b to the x, then it is exponential. Well, let's do that. So this is actually 4, and then if I distribute the 3 here, that'd be 4 to the 3x minus 6 power. Right. And then using some properties of exponents, see how I have subtraction here, 3x minus 6? Well, the only time you subtract exponents is during division, dividing by things with the same base. This is equivalent to 4 to the 3x power divided by 4 to the 6th power. Right, that would be 4 to the 3x minus 6, right? Numerator power minus denominator power. Okay, and then 4 to the 3x, that's multiplication, 3 times x. When do you multiply powers? Well, that's when you have a power to a power. That's 4 to the 3rd to the x. Right, and then don't forget we have the divided by 4 to the 6th power here. Okay, so now, what is 4 to the 6th power? Just do that real quick. That's pretty big. I'm just off to the side here. 4. I know you can't see what I'm doing, but 4 to the 6th power is 4096. So what we have here at the very end is this. F of x equals this 1 over 4 to the 6th power. That's going to be my initial value. 1 over 4096. All right, that's the 4 to the 6th power in the denominator there. Times, and then we have b to the x. 4 to the 3rd is also big. That's actually 2 to the 6th power. That's 64. All right, 64 is 4 to the 3rd power to the x. And do you see how now I've taken some properties of exponents? I had this numerical base with a power that had a variable in it and rewrote it in this exponential form just to see that it is indeed an exponential function. Right, the value of a, right, that initial value is this fraction here, this 1 over 4 to the 6th, or 1 over 4096. And the value of b, right, is that positive base, b to the x. It's 64. All right, and I'll show you with the Desmos site again that these are indeed equivalent. Right, these are indeed the same function. So let me click over back to that Desmos site. And I'll put y equals, since I'm doing two different functions, I'll just use y. Y equals, what they gave me was 4 raised to the 3 times the quantity x minus 2 power. And do you see that initial value? Well, it says 0, 0. That shouldn't really be on there. See, it's technically a little bit, it's a little above the x-axis. See, it's 0, 0.00024. That's the 1 over 4096, rounded to 6 decimal places. All right, it's just so close to 0 that when you're zoomed out, it says it's 0, 0. Right, but if you zoom in close enough, as you saw, it's not actually on the x-axis, right? The x-axis should be a horizontal asymptote. This graph is approaching the x-axis as you go to the left. And I'll put in that other one that we had, what I ended up with after using properties of exponents. It was 1 over 4096 times 64 to the x power. And you see it's exactly the same graph. And if I turn this off and on, you can see it's right on top of the other one. So same inputs, same outputs, and everything. All right. Okay, wonderful. All right, so this is an exponential function because it can be written in that form a times b to the x, where a is not 0 and b is positive. Okay, now the next example. I know that was a long first one, but we just got introduced to this stuff. The next example, we have a function, g of x equals x cubed. Now you may recognize this as a polynomial function, right? And polynomial functions are not exponential functions, right? And again, very easy to tell. This is different. A polynomial is, or a power function is different than an exponential function. Exponential function, you have a numerical base and a variable exponent, whereas in a power function or a polynomial here, you have a variable base and a numerical exponent. Right? It's the other way around. Right? So that can't be written in this way. So not exponential. You could also tell from the graph. Right, I won't go to Desmos for this one. You should know what this looks like, right? Remember, f of x equals x cubed looks something like this. There's, the domain is all real numbers, but the range is also all real numbers, right? But that's not going to happen for an exponential function, right? A function like this a times b to the x, is going to either have all positive numbers as the range or all negative numbers. It depends on the value of a. But here the domain is all real numbers, the range is all real numbers. That's not exponential. Same thing with the asymptote. There's no horizontal asymptote, right? So you can tell a lot from the graph as well that it's not going to be exponential. All right, now for the third part, we have h of x equals 1/3 to the x power. So you got a equals 1. This is 1 times, and then b equals 1/3 to the x power. It's in this form. This is exponential. And if you look at the graph, right, and I'm just going to go back to Desmos for all these exponential functions, it has the shape of all those other exponential functions. All right, we have y equals, it was called h of x, but y equals, parentheses 1/3 to the x power. And you do see, hopefully, now again, remember when a was positive and the base was less than 1, right? 1/3 is less than 1 to the x power like this, the graph was decreasing. But still, the x-axis is a horizontal asymptote here, right? The graph actually isn't touching the x-axis, right? Let me zoom in a little closer until you see. All right, you see eventually that green graph is above the x-axis all the time. All right, it doesn't actually touch it, even though it looks like it's touching it here. If you zoom in close enough, you'll see it's not. The x-axis, y equals 0, is a horizontal asymptote. But the graph is only approaching that to the right end, right? Not the left end. Right? The left end, it's going to the output's going to infinity. But it has that look of an exponential function, right? Domain is all real numbers. Range is all positive numbers. Right? Got a horizontal asymptote, just like all these other exponential functions. Great. Now, this last example in this first part, j of x equals -2 to the x power. This has this form, but the base is not positive. and that's a problem. All right, that is a problem. The base is not positive, so this is not, by our definition, exponential, even though it looks like it is. Right? It has the same form. A is 1 and then times some number to the x power, but that number is not a positive number. And the reason a negative base is a problem is, what about like -2? What if you plugged in like a half for x? That would be the square root of -2. Remember, anything to the half power is square root, and this is not real, right? So 1/2 wouldn't be in the domain. You couldn't plug in a half, right? And the same thing would go for any fraction that has an even denominator, right? If you plugged in a half, a fourth, a sixth, an eighth, 3/4, 5/2, whatever, this would be a non-real number. So that messes with the domain. Remember, for these exponential functions, the way we have defined them, the domain should be all real numbers. You should be able to plug in any real number and get a real number output. But when the base is negative, that doesn't happen. And let me show you, like, when you go back to, say, any graphing calculator like Desmos again, if I put in, y equals -2 to the x power, you see what happens? Look at that. It's weird. It's very, very strange. It's not defined for all real numbers, and it bounces around. See how it bounces back and forth from being positive to negative, because what, -2 to the 0 would be 1, right? You have 0, 1. But then -2 to the first would be -2, right? -2 to the second would be +4. -2 to the third would be -8. -2 to the fourth would be +16. It bounces back and forth from negative to positive as you increase by 1, increase the input by 1. And again, you plug in a half or whatever. I'll make a table for this. So you get all these positive and negative alternations, alternating values. But yeah, you plug in a half and then it's undefined all of a sudden. Right? You plug in a quarter, you plug in a sixth, an eighth, undefined. Any fraction with an even denominator would give you an imaginary output, not real. So it's undefined here, right? If the output's not real, they're just saying undefined. And if I plug in a third, you get something, right? The cube root of -2, that's real, but still, it's just not nice. It's not clean. All right, so that's why we're not going to consider exponential functions to have negative bases, right, like this. So I hope that makes sense. All right, now the next page is more of the same, so it should be a little quicker. I'll go through this a little more quickly. So page 2, example 2, just again the same thing, just identify if you have an exponential function or not. Can it be written in that form? F of x equals or y equals a times b to the x power, where a is not 0 and b is positive. That's all you want to see. Alright, so this is not exponential. F of x equals 2x squared minus 3x plus 1. This is actually another polynomial function. Alright, this is not an exponential function. I hope that is clear. Alright, very easy, that one. Here, this is in that form. The value of a is 1. The value of b is positive 0.875. Right, or 7/8 if you write it as a fraction. But you have a that initial value a is not 0, and the base is a positive number to the x power here. This is exponential. Right, and if you were to look at a graph of this, you'd have domain all real numbers, range is all positive numbers, it has the x-axis as a horizontal asymptote and all that junk. And since a is positive and b is less than 1, the graph will be decreasing as you go from left to right, something like that. Right. When a is positive and b is bigger than 1, you've seen that it's increasing from left to right. Third example here, h of x equals 1.75x plus 2. This is a linear function. Every time I increase x by 1, the output would increase by the same amount, 1.75. Not the same percentage, but the same amount. And that was a linear function. This is not. I'll just put not. Right? Not exponential. And then this last example here, j of x equals 1095.6 raised to the negative 2x power. So again, if you see a numerical base that's positive, and you see an exponent with a variable to the first power like this, this is negative 2x to the first, this is exponential. It doesn't look like this form yet, but as I did with an earlier example, we can use some properties of exponents to write this as that exponential form. This is 1095.6, and then to the negative 2x power is to the negative 2 to the x, right? Power to a power. You would multiply those, get the negative 2x power. And then remember, anything to a negative power is just the reciprocal of the positive power. So this is 1 over 1095.6 to the positive 2, right? And then to the x. So you see that the value of a is 1, right? This is 1 times this. Right? The value of b is whatever this is, 1 over 1095.6 squared. This is a positive number, right? Raising to a negative power is still a positive. Taking a positive number to a negative power is still a positive number. So this has that form where a is 1 and b is, again, whatever this 1 over 1095.6 squared is, and then to the x, right? This is exponential. And again, for a shortcut, you really don't have to use properties of exponents here. You can just recognize, hey, there is a positive number in the base, and there's a variable to the first power in the exponent. It's going to be able to be written this way. It's going to be an exponential function. Great. All right, then for my last examples, we have the following instructions. We're asked to identify whether the statement represents an exponential function or not. So here, the average annual population increase of a pack of wolves is 25. So this means that, this amount of wolves, this average annual population of wolves, this means the amount increases by the same amount each year on average, right? But this whole increasing by the same amount every year, so like one year say it's 100, and then the next year it's 125, and then the next year it's 150, then the next year it's 175, and so on. That's a linear function, right? Linear growth. That's linear growth, right? Increasing by the same amount every time, every year. That's linear growth, not exponential. Right? And again, I talked about this briefly earlier, right? Increasing by the same percentage each year, or the same percentage, in each amount of time. That's exponential growth. So this is not exponential growth, not an exponential function. And hopefully it's very easy to recognize that when given a scenario. So like in example 4, the value of a coin collection has increased by a percentage. See, it's increased by a percentage annually over the last 20 years. So again, the amount, which is this value, amount increases by the same percentage, not the same amount, every year. And that's key, right? Increasing by the same amount all the time is linear growth. Increasing by the same percentage each time is this is exponential growth. And I'll give you a little example here with some numbers I'm just going to make up, all right? So for instance, if we started with 100, right, say the value was $100, then the next year it would increase by 3.25%, so it'd be $103.25, right? Because 3.25% of this would be 3.25. Add 3.25. But then we get 3.25% of this added on, right? So you're not increasing by 3.25 every year. You're not increasing by the same amount. You're increasing by the same percentage, right? So I'd be taking this amount and multiplying by 103.25 again. Right? Let me do that off to the side, and I'll write the result here. All right, so when I take this and take 3.25% of this and add it on, we get about $106, and say if I round to the nearest cent, it would be to the 61 cents, which isn't, again, if I added 3.25 again, it would be $106.50. But I'm not adding the same amount. I'm doing the same percentage every year. So I increase this by 3.25% and then increase this by 3.25%. So multiply by 1.0325 again. And again, I'm just doing a calculator off to the side. If I do that again, then the next year the value would be $110.07. And then I do it again, multiply. So again, it's times 1.0325 times 1.0325. So really what's happening in linear growth, you're adding the same amount every time, right? Plus 25, plus 25, plus 25. In exponential growth or exponential functions, you're multiplying by the same value from one year to the next. Or every time you increase the input by 1, you multiply by the same number. So you'd have a 1.0325 to the t power for time in years, and then times the initial value is 100. There's my function of time here. If the initial value was 100, and then I'm multiplying by 1.0325 each time. We'll talk about more how to write exponential functions in later videos, later in this text, of course. All right, and then my final example, a very simple one, for this. The height of a projectile at time t is represented by this function. Clearly not an exponential function. This is a quadratic function. Right, you've seen quadratic functions in previous videos of mine and earlier in this text. This is a quadratic function, a times t squared plus b times t plus c. This is not exponential, clearly. Right, and if you were to graph this, it's definitely not got that horizontal asymptote. The domain's not all real. The domain's all real numbers, but the range isn't all positive numbers or all negative numbers, like an exponential function would have. And it definitely doesn't have that horizontal asymptote that an exponential function would have. But I leave it to you to look at the graph. All right, and that's it for this video. That's all the examples I have. So again, the key is recognizing this, recognizing when can you write a function in this form with a non-negative initial value, or a non-zero initial value, sorry, and a base that is positive, but also not 1, right? You saw way earlier that when the base is 1, you just have a graph of a horizontal line, right? That's not interesting at all. and domains all real numbers. The range could be all positive numbers or all negative numbers depending on the value of a. And if there's nothing added to it, then the horizontal asymptote's just the x-axis. Great. And I'm hoping that watching me go through these several examples here helps you out when you're asked to identify whether a function is exponential or not on your own. And thank you very much for watching.